Perfect. Excellent. Thank you so much, Morale. Like you said, I'm Sylvia Howland from Cerebras Systems. I'm one of our machine learning solutions engineers, and I do a lot of work supporting the good folks at Argonne and by extension, ALCF users for our systems. Speaking of which, um, so like Morale said, the hardware available at ALCF is going to be our wafer scale engine 2, or CS2 for short. Um, these specs are smaller than the latest generation of our hardware, the CS3, but we're proud that they are logically equivalent. You can run the same workloads on both. So I'll be sticking to the CS2 um, since that's what we'll be using for the hands-on sessions and all of that. We've got 850,000 cores for sparse linear algebra, good meat and potatoes for machine learning. Um, Really key, though, for ML workloads, we have 40 gigabytes of on-chip memory per chip, 20 petabytes per second of memory bandwidth, and then 220 petabytes per second of fabric bandwidth. So we can do crazy amounts of data movement very, very fast. The reason this is helpful, um, or rather, specifically for the unit deployments themselves, because we have this, we're proud to boast cluster scale performance on a single chip, single device. You can essentially take these CS2 racks, deploy them into existing industry standard racks in any sort of data center, compute center, all that good stuff. And we like to make sure these are available on premises or remote and increasingly in the cloud. And so the CS2 hardware that's available at ALCF is the exact same hardware as a larger scale cluster we have called the Condor Galaxy One AI supercomputer, which is going to have 64 of these CS2 nodes, whole bunch of crazy parameter memory up to 82 terabytes. Um, and so we're really proud of how scalable and straightforward it is to operate with the CS2s and CS3s at the user level, which we'll be touching on more as we get into the software stack. But in terms of how things actually operate, where we can get these crazy performance numbers and really leverage this, essentially in the center, we have the CS2 wafer itself. Each of those little red rectangles is representing one of those 850,000 compute cores I mentioned before. Each of those is going to have, obviously, its own compute power, but also its own essential distributed memory cache. And all of these compute elements, or processing elements, we call them, are going to be communicating to their neighbors. And so we are able to distribute our data, our parameters, and our compute in this very synchronized, sort of elegant symphony of distributed compute, distributed communication. The way we're able to achieve such high levels of model scalability are in large part because we've actually disaggregated memory, compute, and then data storage. We've co-designed basically every aspect of the ecosystem that interacts with the CS2. So the CS2 itself, right, crazy amounts of memory bandwidth, large amounts of compute. Historically, on a GPU, right, we're going to be storing all of the model parameters in GPU memory, or we're coming up with some technique to parallelize sort of which layers or which parts of which layers are sort of resident on a GPU at any given time, and then trying to figure out our scaling logic from there. With the CS2s, we're happy to say you store all of the parameter weights off wafer on an external parameter server. We actually stream those weights one layer at a time to the CS2s, at which point we're also ingesting data, running our computations forward and backward paths, and then we stream everything back to our parameter server, which traditionally would be extremely slow, right? Streaming all of our weights one layer at a time. Normally under the old paradigm, not a super good way of doing things. The reason this works, right, is as we mentioned before, that crazy amount of memory bandwidth. This actually renders it quite efficient to stream potentially a very, very large weight. I think the estimates of what we can sort of handle on a CS2 are something like 100,000 by 100,000 unit dense layers. And the size of the rest of the model is irrelevant in this case, which I always find to be quite exciting. And so to reiterate, essentially, we have this memory X unit, which is that parameter server on the bottom right. And the only thing that needs to store is all the central copy of the model weights, and then have just enough compute to do optimizer math, which is much lighter than what we need to actually perform forward and backward passes on the model itself. We stream all those weights out one at a time. We specifically only store the layer activations on wafer after each layer, because that's all we're going to really need to perform our backwards pass. And so there's a little bit more to it than this, but for the sake of time, we're able to cleverly sort of cache only the barest amounts of memory on wafer we need to continue moving at a blazing fast speed across the entire forward and backward pass. Another thing we really pride ourselves on is how intuitive and straightforward our scaling is. Right, if we think about the code we're going to need to implement to run, say, a transformer model on a single GPU versus 4 GPUs versus 1024 GPUs, the software infrastructure and engineering expertise that comes along with that can get very, very intense very, very quickly. In our case, when we're scaling up to multiple CS2s, the actual workflow looks very similar from a hardware perspective, right? The only thing that's different is in between the memory X central weight server and however many CS2s we're using, we have this additional swarm X, essentially, interchange layer that's going to enable efficient broadcasting of weights and reduction of gradients across all the CS2s. And we can recognize this as a pretty straightforward form of data parallelism. Each CS2 only cares about the data that it's getting in and the gradients that it's firing back to the swarm X that's handling all the distribution and aggregation. Because we can move so much data so quickly across this entire flow, and because our on-chip memory is so large, and the fact we don't need to store all the model parameters on every wafer at any time, again, we're just doing one layer at a time. What this lets us do is we can program our execution such that no matter how many CS2s we're working with, right, we're using the same overall system architecture, this exact same network execution flow, and most importantly for users, the exact same software interface and the exact same logical interface, which we'll be getting to. We always say the difference between executing a model on Cerebras systems for one node versus 128 nodes is literally just a one-line change in your dispatch script, and then everything else is handled under the hood. It's not something ML practitioners need to worry about. We don't want science problems to become supercomputing problems all of a sudden. Perfect. And then in addition to the hardware, sort of like one layer above that, we do also have our Cerebras SDK, which is not even necessarily machine learning focused. This is a general purpose parallel computing platform and an API we've set up that let software developers of many stripes write really low-level programs or kernels for our systems. When we talk about those 850,000 processing elements distributed in that sort of grid mesh data flow structure, this gives folks an opportunity to code and implement applications on that level, that sort of very low-level data flow. Comes with all sorts of tools. We have our domain-specific Cerebras software language and then some Python API bindings as well. In terms of case studies, right, this is all well and good. Numbers are high. The design seems elegant. What can we use it for? Here we have a couple of Gordon Bell winners and finalists. In 2022, we were able to contribute to some award-winning research, specifically using genome-scale large language models to analyze the evolutionary dynamics of COVID-19. We were operating using over 10,000 sequence length or sorry, 10,000 tokens like sequences, um, which really made it possible to analyze these genome scale problems in ways that couldn't be done before, especially at a critical time, right? We think 2022 pandemic was not yet sort of rolling back the way it is today. Um, Additionally, last year, we were able to process novel seismic processing loads using CS2s. Um, Something, again, because our unique architecture gives us certain unique advantages. We have this graph at the bottom right, 48 CSs, right, able to achieve real memory bandwidth performance that is on par with the Fugaku supercomputer and outpacing something like Frontier. There's a lot, it turns out having really high, crazy memory throughput enables you to do all sorts of fun supercomputing applications, in addition to the obvious machine learning applications that are our bread and butter. Perfect. We're also dedicated to open sourcing as many models as we can. Basically, whenever we work with a customer, we produce some sort of model with them. There's always the proposal whether they'd like to open source it. We have, just for instance, this is not comprehensive. We have our Cerebras GPT family of large language models that we've trained in a compute efficient manner. Internally, something we're very invested in is doing lots of scaling experiments and making sure that we're using our compute budget wisely, transitioning from small scale experiments to large scale production level runs. We had a state-of-the-art 3 billion parameter open source language model, this BTLM, and then Jace is more recent and is the world's best Arabic English language model that was produced in our partnership with G42. We're very proud of that. We've learned a lot about multilingual modeling from that experience. And then there's many. Excellent. So before I move on to the software stack, I wanted to add that relatively hot off the press, we also have a finalist for this year's Gordon Bell Award that was focused on really highly scaled and efficient molecular dynamics. When all was said and done, I'm not super familiar with the details of that work, but I do know that the level of performance we were able to achieve on these MD simulations was faster than you could realistically achieve with more or less an arbitrary number of GPUs. And I think is a good example of sort of how people can leverage the throughput, the high performance, the straightforward scalability of our systems to advance all sorts of applications from AI to scientific computing. Perfect. So moving on to the software stack, we've gotten a better understanding of what the hardware looks like. Our philosophy is relatively simple. When you are developing on a Cerebras system, we want you to be able to develop in PyTorch and then just execute on the CS system. We try hard to make this as dead simple to run as possible. When we're defining what our model looks like and what its logic is, you program this the exact same way as you would with a single GPU, with a couple caveats. There are some like drop-in replacements for certain PyTorch utilities, but overall we try and preserve as much of the PyTorch API as possible. And specifically programming the way you would with a single GPU. We don't need you worrying about any sort of distributed compute or parallelism. We've abstracted all of that away and made it as straightforward for you, the user, as possible. Essentially, on the right here, going from top to bottom, we have sort of decreasing levels of abstraction, right? At the top, we have PyTorch, which a lot of ML developers are going to be pretty familiar with. We provide a model zoo with all sorts of reference model implementations and utilities, which we'll get into shortly. You're going to have some model script that's, again, defining logically, more or less on a single GPU, what your model would look like. And then below that, we have a slightly lower level layers API that's a little less batteries included than our sort of reference implementations and utilities, as well as a whole bunch of pre-implemented ops for our Cerebras graph compiler, at which point, right, things get lowered down another couple levels of abstraction. We have both a hand-implemented kernel library for our hardware, as well as some kernel auto-generation capabilities. If what you're trying to execute can be supported by combining pre-existing kernels, we'll automatically try to stitch those together in a way that will support your model. And then that goes through our very sophisticated placement and routing engine, right? Because we think about all of the ops and orchestration that has to go into training. For example, a large language model across, again, on a single CS2, 850,000 of these communicating processing elements. But once all that is done, what is on its surface a pretty straightforward logical definition of our model in PyTorch has been fully mapped onto the wafer scale engine, and we're ready to take advantage of that straightforward scaling, that blazing fast throughput. Speaking of that model zoo, that more batteries included approach, we have a GitHub repository for it there, github.com/Cerebras/model zoo. It's a great starting point. We have a bunch of model reference implementations, everything from BERT style models to GPT-3 to Llama 3 to Mistral, things like that. Also, all sorts of examples of how to prepare your data, even do things like convert to and from popular Hugging Face checkpoint representations. We try to be interoperable with Hugging Face specifically, because a lot of people will, for instance, train using CS2s and then serve with a different form of model checkpoint, try to be interoperable in that sense. Everything that we've included in the model zoo are implementations we've vetted and tuned to be as optimally performant as possible. And the model zoo isn't just sort of an archive of models you can pull off the shelf and immediately start using. We also like to encourage folks to use it as a way to develop new models. For instance, the model zoo is built on top of our CS Torch API, we call it. It's essentially just one step above. It's a wrapper around it. If you want to extend the models that are in Model Zoo using that API, you're totally welcome to. Like I said, we try and match to PyTorch pretty heavily. And it also provides examples of how you can organize your files as a template for starting your own models and hooking into that Model Zoo logic. In terms of what that directory might look like, they're all going to have this run.py script, which is essentially going to be the entry point into the underlying Model Zoo logic that's going to handle the training and eval loops on your CS2s. If you need to run a custom training loop, we do support that as well. It's a little bit more sophisticated, but it's possible to support more or less arbitrary training loops using that PyTorch API. You're going to have a bunch of configs under a subdirectory that are going to take the form of YAML files. We'll touch on those in just a moment. And then we're going to have the logical definition of our model, and then any sort of logic utilities or data utilities we need to get things up and running. Excellent. So in terms of what it looks like to actually program and train on the cluster, like I said, we essentially write our model in vanilla PyTorch, defining all of our layers, all the flow, all that classic stuff. And then on the top right, we have an example, just a little snippet of a model parameter YAML file, which is going to contain all the information about what data we're using, what data processors we're loading in to handle it, the model structure in this case, for instance, like your classic hidden size, number of layers, number of attention heads you're working on, and defining all those in the YAML file to essentially parameterize the logical definition we've already spun up. And then when it comes time to train, dead simple. We have that run.py for our model type from before. We just execute Python on that run.py, and then a few key arguments. We want to make sure we're pointing to that YAML file up above, again, to parameterize and specify all the details for the specific model we're deploying. This could be the difference between, say, running GPT-3 with 500 million parameters or 250 billion parameters. That's just a matter of scale. The underlying logic remains the same. And then, like I said before, specifying the number of compute nodes is literally just this third line here, num CSX. That could be 1, that could be 64, that could be 256, depending on the compute available to you. But you don't have to worry about any of that as a developer. and specify the amount of resources you need, how long we're training for, et cetera, et cetera. And then we just execute this Python command and things will run. We have a quick demonstration of what this looks like using a 1.3 billion parameter GPT model just on a single CS2. This is a snapshot of what that YAML file looks like. The details aren't super important right now, but we have our different data processing sections, our model definition optimizer, and then sort of meta level configuration parameters for the run. And then, yeah, we execute our Python run.py. And then we just have some boilerplate up at the front here talking about our effective batch size, compiling everything down to the wafer level, and then just some communication with the cluster to get things written out and ready to go. Perfect. And then once all of our weights are streamed over to the wafer, we are off to the races. Processing, in this case, let me move that so I can get a proper view, approximately 890 to 900 sequences per second. The exact number of tokens, right, depends on our sequence length and our batch size, all that stuff. So that's sort of a basic example of how to get things going on the CS2. There's a number of features we think are quite nice that we also enable, one of which is sparsity accelerated training. If there's one thing a lot of people know about large language models and similar neural networks, is that they are, in principle, super over-parameterized for the problems they are being trained to solve. This can lead to a lot of wasted compute if a lot of those weights are not actually influencing the logic of the model's calculations overall, or if a lot of those weights are dead, as is the case with like a classic ReLU activation, where a bunch of your weights are just going to be set to 0 all the time. Anyway, just because of the activation. Unstructured sparsity, which is to say arbitrary pruning of weights, opens up a whole other angle for improving models. Ideally, sparsity would improve training efficiency. We could basically skip over parameters we don't need during training and eval. This would let us hit either the same accuracy with less compute and effort during training, or we could take the same compute budget and ideally train a higher accuracy model by just understanding the sparsity we can eke out of the model. Ideally, we could be able to do both. Sparsity is something that has been a growing research area, both in the ML community writ large, but also at Cerebras for quite some time. And a nice thing, remember, we're streaming all of the weights from a layer more or less individually onto the wafer. This means if we have a model that is sparse, and there are weights that we know are pruned or are just going to be 0 all the time, we can just not stream those over, right? We can just not spend any compute on them. And so I won't play the full video necessarily for the sake of time, but this means we offer very straightforward application of sparsity in our models, and you just get free acceleration, essentially, for having model sparsity, even unstructured, again, arbitrary weights being pruned like this. The only real change you need, if you can see the line that's highlighted, has sparsity in our YAML configuration. And really, we're just specifying the type of sparsity we'd like to perform, the degree of sparsity, in this case, 90% weight sparsity, and then just initialization methods, all that kind of standard stuff. If we then wanted to train the sparse version of our previous model, there's literally nothing else we need to do. We execute the exact same command. And then instead of executing, say, oh, my bad. Instead of executing, say, 800 sequences per second, again, for free, we're up to almost triple that amount just by executing that degree of sparsity, no other sort of considerations necessary. And also, like I mentioned before, scaling to multiple CS2s, incredibly simple. We just change the number of CS2s or CS3s, whichever hardware you have access to. in our dispatch script, and then we handle the rest. That all gets distributed out with essentially linear scaling. Perfect. And then this also won't necessarily take time with the full video, but we can see at the very top, we've just specified 16 CS2s instead of 1. And then instead of processing about 800, 900 sequences per second, we're up to about 26,500. And that's probably not as high as it would be, especially at the beginning of a run. Average performance tends to increase as things get sort of burned in. The first few iterations can be a tad slow. Perfect. So like we said, again, the fact that we can just use data parallelism essentially very naively, but also very optimally, given the nature of our hardware stack, allows us to, again, scale linearly with the number of systems, which is very nice. It makes it easier to reason about compute costs and time estimates, knowing that if I double the amount of systems, I'm going to get more or less very nearly double the amount of throughput. Excellent. Like we said before, also easy to scale to larger models. If I wanted to take a model I'd already parameterized and just make it larger, I can copy that YAML file, figure out what changes I need to make to number of layers, hidden size, any other model-specific parameters. And we don't have to touch the actual code itself in order to scale, just the parameters. That's the specification, essentially. Excellent. So that's like a quick sort of how-to high-level overview. We also have docs.cerebras.net, which is going to have access to all of our introductory documents, some comprehensive tutorials, a bunch of more specific how-to walkthroughs. I'm proud to say we're also in the process of revamping and continue to refine a lot of our documentation. We're definitely valuing our user experience and trying to make this straightforward as possible. We know it can be a different environment moving over from a traditionally GPU-focused paradigm. So we're committed to documentation, case studies, all these sorts of things, especially with the folks at ALCF. I work with them pretty closely to get more of those spun up so that if you have a custom model that's maybe a bit weird, that we'll be able to port it over to the CS2s without too much headache. Perfect. And then to cap things off, if you ever want to contact us, you can always email us at developer@cerebras.net. We have a monthly newsletter at info.cerebras.net/subscribe. And then I won't read out the Discord links, but we do have Discord and Discourse where you can talk to other researchers as well as our own ML and our SDK engineers. And you can always find us on LinkedIn and Twitter/X. Thank you. Oh, I cannot really hear us in the room if someone is speaking.
Oh, thank you very much for the wonderful talk. I think the biggest questions in the audience in the room at the moment.
Yes, I have a question. Thinking about scaling. So you show scaling in terms of number of systems, but if you have a smaller model size, say like in millions of parameters, and you can fit multiple models per wafer, are there any tests on how that scales? And how would you compare it to scale to distributed training on the GPU?
Are you talking, so to make sure I understand, is the question about how different sizes of models scale across multiple systems?
If you're doing it on a single wafer, but you're looking at a smaller model size, so you can fit like multiple models per wafer.
Oh, this is an excellent point. When we talk about decoupling compute from memory, the only sort of memory consideration that matters is how large of a model we can fit on that external parameter server. If the model is smaller, we can absolutely map in probably like more data at once on the wafer because we'll have more memory to play with. But at a certain point, right, we don't necessarily need as much compute to process smaller models. So we would expect to see, again, linear, sorry, I'm not phrasing this super elegantly, but the answer essentially is the way we compile a smaller model onto the wafer and understand how the compute flow is going to go is different than how we would for a larger model. But because we're only storing individual layer activations on wafer, there's not really a distinction between large and small models in that way. Whereas on a GPU, usually larger chunks of the model are going to have to live on device. For us, because the memory throughput is so high, essentially all the major memory concerns are operating off wafer on those CPU memory X servers, if that clarifies.
Thank you. So let's follow up with that then. So besides being able to do larger data sizes, is there an advantage to training a smaller model which would fit on a single GPU on the way?
If all you were doing was training a very small model that fits just fine on a single GPU, you probably have a very similar experience. A lot of our value add comes from when it is time, or if it is time, right? Not all use cases need this, to scale up, either in terms of amount of compute via very large batch sizes, or via model size. Things like move parameter optimization allow you to do a lot of experiments at smaller scales and derive sort of optimal hyperparameters for a larger scale version of the same model. This is something we're able to do quite successfully internally in our collaborations. At which point being able to just plug in additional compute to scale the model really pays off. But aside from just model size, another thing that our hardware stack enables very elegantly is very, very long sequence lengths. I know at this time we're working on dialing in our throughput for hundreds of thousands of tokens. So even if you're training a small model that would fit fine on a single GPU, there are things like sequence length, ease of scalability, etc., that I think the CSXs bring to the table that are quite compelling.
Thank you.
Just to kind of follow up there, could you maybe give us like some like rough guidelines for when we should maybe start thinking about making that transition from like a GPU based training over to a wafer scaling? And we have a lot of people who are trying to scale up a lot of models for the scientific applications. What would you say like is the rough point at which it starts making sense to switch? Either like model size or like number of examples. So
Yeah, this is an interesting question because I see this as almost more of a like paradigm question or like an inertial question rather than like a purely theoretical one. In principle, if you feel like your project probably needs to scale up at some point, I think there's value in getting used to working with a wafer scale paradigm sooner rather than later. Again, because as you go from like a 500 million parameter model, if you know you're going to be operating in even like several billion parameter space, it can be useful to know that all you have to worry about is the like derivation of hyperparameters and knowing that the scaling is going to be super straightforward. That's sort of my line of thinking. Obviously, if there are certain like more familiar libraries and utilities that exist in the sort of NVIDIA ecosystem, it probably makes sense to like explore with those early on. But myself, obviously, as like Argonne's main solutions engineer on the Cerebras side, I'm always interested in figuring out sort of what folks' needs are. So we can work with engineering to support workloads that are in demand. So this is definitely a like dialogical process where if you have problems you think would benefit from a wafer scale approach, you also don't have to purely think about it internally. We're always happy to talk and figure out what any obstacles or potential upshots look like.
Okay, well, thank you. I don't think we have any other questions for participants, so I think we're gonna be moving on to our next talk, but thank you very much for just giving us a great rundown of Cerebras and how it fits into training larger models.
Absolutely.